Okay, now I would like to continue. So last week we have um, discussed on the area of polar. So let me continue today, filling up the arc length and the tangent. So arc length in polar. So we start off by taking the conversion for the xy, and then we say that we have the r cosine theta and r sine theta. And then let's derive this with respect to t. So derive with respect theta. So this will be dx d theta. And r we count r as another variable. So let's say this becomes dr d theta. So we have a product rule now. So cosine theta, and then it's minus r sine theta. Okay. And then the same thing with y. So dy d theta. This will be dr d theta sine theta. And then because sine derived become positive cosine, is positive r cosine. So what do we want is we treat this polar as in the parametric for the arc length, like we did previously. So we want to make this, So let me write this first and then see what we can do about this. So we have dx d theta squared and then dy d theta squared. Now to get this simplified for dx and dy, so let's start by taking this dx d theta squared. Okay. And then taking the dy over d theta, another squared, which means we are going to have a quadratic expansion. Okay, so it's long, but it will be I think it will be helpful. So let's just write all over. So this will be dr d theta squared cosine squared theta minus 2r dr d theta cosine theta sine theta plus r squared sine squared theta. This is only for the x, right? This one. And then plus the other one, dy d theta squared. So this will be the same, dr d theta squared. Let me put here a little bit lower there. Okay, and then this will be sine squared theta plus 2r dr d theta sine theta cosine theta and plus r squared cosine squared. Now if you see, we can simplify our equations. So this will be dy d theta. So you see that this one here we can cancel. So let me just make line like that. So cancel. And then we have this. I can factorize dr d theta squared. Okay, and then also the r squared. And then all the cosine squared plus sine squared will be reduced to 1. Okay, our basic identity. So we are going to have all of this become just this. So we can simply, for polar, we could just write the dr over d theta squared plus r squared. Okay, so we can substitute this to here, which resulting in this one. So it's quite straightforward for the formula itself. So as long as you know the formula, you derive the formula with respect to theta, and then you can just put into these positions, and then basically that is the arc length. This is the arc length that we discussed in parametric. So this is just how we convert the parameter to the polar. To do that, we just take the conversion on x and y. This? Because this is a function of theta.
If I want. Okay.
Yeah, it's a function of theta. So this is for polar curves. So you are usually given r equals something, or you need to find what is the polar formula. Usually it's r equals something variable with theta, right?
It's going to be given.
Yeah. Usually it will be given.
Usually?
Yeah, usually. But most of the case it will be given.
How can I find it?
Well, depends. Sometimes if you are perhaps a parabola or perhaps a circle, then you can rewrite in the polar for circle. For example, the circles equals the constant. Yeah. But usually given. Usually given. Okay, let me zoom out a little bit just to see some example here. Find the length of the cardioid 1 plus sine theta. Okay, if you want to draw the cardioid, it's okay, you can draw to help. But if you know how and you would like to just compute the exact length of the curve, then you can go ahead. Okay? Sometimes if you're familiar with the curve, it will be straightforward questions, so you can just answer it. But if you need to draw, then you can draw. And remember, this is not an xy, this is a polar. So you could imagine that the r1 plus sine theta, let's say sine theta is from -1 to 1. So it's going to be, the radius will be between 0 and 1. So 0 is still on the center, right? And then the maximum will be 0 and 2, right? 0 and 2. So let's say 2 is going to be in pi over 2. Let's say this is pi over 2. This is theta equals 0. This is pi. This is 3 over 2 pi. And we have here is 2. And then when sine is 0, which means here, this is 1, right? And remember, the cardioid for the 1 plus, okay, plus sine. So the large portion of the curve will be in the upper side. So it will be like that, and it will be symmetrical. And then it will be having some loop that going to be looks like a cardio or heart. Okay. Now, if you would like to calculate the length, now because this is going to be a full circle, now we can check within this formula. So basically we take that and the r d theta is equal to cosine, right? So we can just exchange all of that into our formula. And the r will be 1 plus sine theta squared, and this will be plus cosine squared theta, and then d theta. Okay, now let me work here. 1 plus 2 sine theta plus sine squared theta, and then plus cosine squared theta. So the total will be 2 plus 2 sine theta d theta. Okay, if you find this, for example, in exam, you could just bring your calculator, okay? Or if you want to force yourself, and it's quite because it takes time, you can try to so the important thing here is you can have some processes and then have like a final result, the integration, which you can compute using additional tools. But if you want to use your hand, I think one way to solve this is to multiply and divide with. So we call this rationalize the equation. So with this, sometimes it works, especially for trigonometrical integrations. So what we are going to expect is this one. We are going to have, it's like a plus b, a minus b, which is you have the a squared minus b squared, right? And then the square root will be, you can practically see the 4 minus 4 sine squared, okay? And then 4 minus 4 sine squared is basically 4 cosine squared. Okay, you see, so you can and then you can remove the square root after some calculations from here. And then you have cosine over this, which you can substitute. You can use substitutions. Okay, you can use substitutions. You can substitute this, or let me just show you, maybe. Maybe it's too big. Maybe let me resize this. So this will be 0 to pi. So this will be 4 minus 4 sine squared theta. Now remember, here we can make this as 1, okay, which we can y is cosine squared. So this will be 4 cosine squared theta, and it's still in square root, and we can remove the square root and write this as 2 cosine theta, and then we have this. Okay. And then you can use substitutions. But if you forget everything in calculus 1, you can just go here, open your calculator, and type it. The important thing for this topic is the arcline process, okay, not the computations. But suppose that you are going to calculate it by hand, you can just use this. And you can use substitution. Yeah, okay. Yeah. Yeah, this one? Yeah, this one. So basically you just multiply 1 by 1. But since this is a plus b, a minus b, we are going to have a squared minus b. Because this part will be cancelling as we move on. Okay, or if you want, I think from here you can also write some identity for trigonometry, and you can still have the same result. This is, yeah, integration have several ways to get, but I think for your own good in exams, you get this, open your calculator and type. It works for something like this, it works, but for maybe some other theory, maybe not really works. And I hope you can solve this by yourself. Okay. Just use substitution here. Let me just write here. Use substitute u equal to minus 2 sine theta. And then you will see it will cancel. Okay. Now let's continue. So arc line is quite short, not really that much here. So I think you could just focus on this formula, okay, this formula, and you can work with all the arc line in polar. Okay. Now let's move a little bit to the tangent. So tangent, we tried. So we have derived both of dy and dx from the previous one, And then since we know that the tangent in parametric we can work like this, okay? Then the idea is basically we can basically for the tangent we can treat using this polar equations, this one here. This is polar derivative. Or you can just use basically your parametric. So you can have like a two choices. Both will be resulting the same way. Okay. So basically, what you are going to do is, this is expecting that the you have given the r equal function theta. So basically you can do to this, or you can rewrite your x and y. Basically x is r cosine theta, and then y is r sine theta. And then you can do as in parametric. Okay. Or you could do it from here and then get this formulation. Sometimes when you have like r given, maybe you could just multiply with cosine or sine to get xy, and then you can use parametric. The same result. So let me just go for some example here. So the same cardioid from the same example from the previous example. So let me write cardioid. So that is 2, this is 1. Okay, let's say that's our cardioid. Okay, find the slope of the tangent line when theta is equal to pi over 3. So we could try to find, so let's say this is the r. And then basically we are going to find dy over dx. So you could do this way. You can write the r d theta sine theta plus r cosine theta. Okay, and we can write the r d theta here is just cosine theta. So we can change everything with cosine for the r d theta. So sine theta, cosine theta, and plus r is 1 plus sine cosine theta, and then cosine squared theta minus 1 plus sine sine theta. Okay, let me work here. This will be cosine theta plus 2 sine theta cosine theta. And what we have here is we have sine theta plus sine squared theta. Now I can exchange the cosine squared to be 1 minus sine squared. So I will have all in sine. So I will write the bottom part is negative sine, negative 2 sine squared, and then 1 negative 2 sine squared theta minus sine theta. Or maybe let me write sine theta first. Okay. And then this will be cosine theta. I will factor out. Okay. And this is practically, this is a, if we have a to a squared. If you confuse, you can do this. This is a, I think, a quadratic, right? This should be 1 1 1 and maybe 2 negative 1. Oh, it should be 1 negative 2. So if we cross multiply, this is okay. So this will be 1 plus sine and 1 minus 2 sine. I think we can just stop here, or if you want to stop up until this one, I think still okay, because our goal is just to take the slope at some angle, right? The angle is pi over 3, so let's just put pi over 3. Okay, so dy dx, and put the theta is pi over 3. So basically we just change the input. So cosine pi over 3, it will be half, right? And then 1 plus, it's half square root of 3, so it will be square root of 3. And then this will be 1 plus, and then 1 minus square root of 3. And then you can just calculate easily. Can exchange, I think you can exchange this to 2 plus, right? And this, oh, this cancel with that. So let's check this too. So it should be 1 plus square root of 3, and this will be negative 1 negative square root of 3. And then the same questions as in the parametric. Finding where the tangent line is horizontal or vertical. So basically that is going to be so dy dx is this, right? Horizontal when dy d theta is 0, and vertical when dx d theta is 0. So basically you need to solve the polar equations on this dy d theta and dx d theta and find the possible theta, okay, the possible theta. But since we need to adjust the theta, okay. So horizontal is when this is 0, vertical is when this is 0. Can we have some situations where both of these zeros? We might have, right? 0 over 0. We can, right? We can have, right? Okay, so this is maybe it's, I'm just taking too fast. Maybe here what I mean is you find the theta, okay? You find the theta here. You have several theta, right? When you check back the theta, check back through the equations, sometimes it works because there are maybe some of the differences, but maybe there are theta that comes up at the same at both theta. Okay. For example, in this case, 3 over 2 will be on both sides. So let me write what's theta here. So theta here is pi over 2, 0 over 2 pi, 7 over 6. I'm skipping the process for finding the theta. I hope you can do that. Okay. Basically just equaling the polar curves and using some trigonometric. Okay. So notice that we have 0 over 2 and 3 over 2 here. Okay. So how to solve if we have these situations? To solve this, remember, whenever you find the 0 over 0 situations, and if you can try to approach the curve using limit, then I think the best way is taking this equation into the limit equation. Okay. So that means since we have this, and 3 over 2 is over here, right? This is 3 over 2. So we can say we can approach limit from the left, from the right, but let's say we try from the left, because it's symmetry, it doesn't matter. Left, right will be the same conclusion. So let's say since at theta equal 3 over 2 pi, dy d theta is 0, dx d theta is 0, then the dy dx, we can try to take the limit as the limit approaching the 3 over 2 pi, let's say from the left, okay, from the left. Okay, now taking from the left, now we are using the limit operations. So 1 plus what is our dy dx? 1 plus 2 sine theta and 1 minus 2 sine theta. So let me write and separate the equations. Let me put on the left. And then limit. And then the other one is this, right? And then we check. If we put at our value, what will happen? I think we might have 0 over 0 situations. I think this one we can just compute, right? For the left one, it will be 1 minus 2 is negative 1, 1 plus 2 is 3, so it's negative 1 over 3 for the left one. And then still in limit. For the cosine theta and 1 plus sine. So what will happen here? It will be 0 over 0 situations, right? So we can do the L'Hopital rule. Okay. So it means that we take the derivative for both the upper and lower equations. So this is negative sine divided by cosine theta, which is going to be tangent, which the tangent are infinite for the 3 over 2 pi, right? So we can say that this will be infinite. And by symmetry, we could see also when we take limit for theta 3 over 2 pi from the right, we would get the negative part. So how it looks like when we have a positive and negative infinity. Let me just get through the picture just to see what it means. So from the left, we see it's going up, right? So it's going there. So from the or even. So let me just write here. Let me clean this up. So which actually it's going to be like that. So it's going to be having some infinite vertical tangent. Okay. So that's going to be this. Okay. Okay, any questions? So just a note, maybe you get confused on this. This part is we solve this and we get the theta is that, and we solve and we get the theta is that. So I think that's chapter 10. Okay, so all finished. So next week we will have a quiz. Okay. Thursday, okay, Thursday, not this Thursday, but next week Thursday. What the date? Let me check the dates.
Professor,
Yes.
can you zoom in with the cartoons?
Hmm?
Can you zoom in?
This one? Okay, we'll have a break. Okay, so don't forget quiz Thursday next week. It will be focusing on chapter 10. Chapter 10. So it means until polar, okay, until polar, calculus polar. So parametric and polar. Okay. So I will move to the next chapter, which is chapter 11, the sequence and series. Okay. So the sequence and series. So we start by taking a look at this example here, which we call the Zeno paradox. When someone walks approaching the wall, and then the rules how he walks is, for example, if this is going to be 1 meter distance, he can walk half of it every taken action. For example, if this is 1 meter, then the first action is half meter. Then the next action is the half of that distance. So 1/4, and then 1/8, and then you can see how much he will count. And the question for this Zeno paradox is, does the person can arrive or touch the wall? So suppose that he can only walk half of the distance. No, right? Okay. But because we're now talking about calculus, and in calculus, the essential concept for every part of it, derivative, integration, all is within limit concept, right? Using limit. So if we are going to cheat using limit, he can touch. Or we can say he is close to touch. Okay, that's the limit. Okay, close to touch. But in the real world, the limit is not really that exists. Okay? The limit is our tool to approximate, so that we can get to close to something. Okay? So that's how it goes. And from that number that we've done here, half, 1/4, 1/8, 1/16, and etc., we can have a pattern that we call 1/2 with power of n. So when n is 1 is half, when n is 2 is 1/4, and you can see 1/8, 1/16, and so on. Okay. Now this is what we call as a sequence. This is what we call the sequence. So sequence is a list of numbers, okay, in indefinite order. So list of numbers in definite order. So usually or generally we write this as A1, A2, A3, and so on and so forth until some AN. Okay. We called A1 as a first term, second term, and so on. Okay. Usually also we can rewrite this by taking this bracket. It means that the sequence of an, or we can write completely by taking the n from 1 to infinity. Okay, we can write something like this. So if we say that we have 1 over 2 n as our sequence, this means that the an is 1 over 2 with power of n, and we can write this as 1 over 2, 1 over 4, 1 over 8, and so on and so forth. 1 over 2 with power of n. Okay? And sometimes the sequence may have an alternate sequence, which means the signs can be positive, negative, positive, negative. Okay. For example, if we have something with the negative 1 with power of n, and then n plus 1 over 3 with power of n. So this could generate, so let's say we start from n equal 1, so, or we say sometimes it's from 1, sometimes it's from 0. So let's say from 0, okay, to make it 1. So when n is 0, so all will be positive, right? And then 3 will be 1, so 1 over 1, so this will be 1. And then n equal 1 becomes 2 over 3, right? But negative, since negative 1. And then we have 3 over 9. And then we have negative 4 over 27. And so on and so forth. Okay. And sometimes we are given the the sequence, and we need to find what is the pattern. Okay, what is the pattern? For example, we are given 3 over 5, negative 4 over 25, 5 over 125, negative 6 over 625, and so on. Now to find the pattern, we can identify this will be A1, A2, A3, A4, right? So if we look at the pattern, the first thing is we have an alternate sequence. Okay, we have positive, so positive, negative, positive, negative. So it should have negative 1 with power of something. Okay, it can be n or n minus 1. Okay, depends on which part we are going to see. Is it negative first or positive? In this case, it's positive first. But then we see that the denominator is starting from 5. The second one is 25. The next one is 125. And then we see that this will be multipliers of 5. Okay, so we multiply by 5, 5, 5, okay, for the denominator. So the denominator will be 5 with power of some n. Okay. Since it starts on 3 over 5, so we assume that n starts from 1. Since n is start from 1, then this negative 1, if we want to say just n, when n is 1, then it will be negative. So to make it positive, we take negative 1. Okay. And then for the top, for the numerator, it's 3, 4, 5. So since n, we say start from 1, so we need to plus 2. So we need to take n plus 2. Okay. And this is our pattern for the sequence. And there are other sequence that is not in the normal rules, like in arithmetics rule or mathematics rule, like a unique sequence like a Fibonacci, which is we cannot really define using these general rules. So we have some unique case we call the Fibonacci. So this should be f1 is 1, f2 is 1, and then fn is fn minus 1 plus fn minus 2. And n should be at least 3, at least 3. So 1, 1, and then 2, 3, 5, 8, 13, and so on. Okay, that is for just introduction. Okay, just introduction. And I think some of you have learned sequence before, right? In high school, or maybe I think in high school. But I think not everyone. So I hope you can catch up the introductory concept for sequence, because basically sequence is just a list of numbers that are in order. Okay, that are in order. Okay, but in our case for this course, this is not the important one. We are going to see at the end of the day, can we use sequence or series to approximate something that we can perhaps, if we have a graph or a curve that maybe we could see some representation in functions, and then we can also represent in terms of the series, which we are going to have later on. So that is our goal. So from the sequence and then later series, we are going to see that some functions can be represented in series. Okay, so that is what we are going to achieve at the end of this topic. Okay. But before that, let's just start with the sequence, and let's see what is our what we can achieve in this sequence. Okay. So we start with the concept limit. Okay. So suppose that we have this sequence. Okay. We have 1/2, 2/3, 3/4, and so on, and we can rewrite that in this sequence formula, n/n plus 1. Suppose that we have this. Okay. So first, imagine that we have a line, okay, 0, half, 1, and this is denotes the terms of the sequence. Okay. So half is starting from here, okay, and see how we can move. Okay. So see how we can move. So first term, and then the second term is 2/3 is around here. So you can imagine this is divided by 3. So this will be 2/3, and 3/4 is here, half of this, right? So 3/4, and then 4/5, and probably 5/6, 6/7, and then you will see that when you have n increasing larger and larger, the distance is getting closer. Okay, this is similar to what we achieved before in Zeno paradox, when he walks and then he tried to touch the wall, but he cannot. Right? It seems that we are going to see, but since this has limitation on pixels, right? So we cannot really see. Is there any evidence that it is touching this one? We don't really know if we just see from our eyes, right? But perhaps the real reason or the real numbers for the n, maybe if n is 99, maybe 99/100 is already 0 point something close to 1, right? Something close to 1. Okay. Now the second visuals that we can also observe is this one. can see from here, this is the a and this is n. Okay, and in sequence and series, or perhaps in sequence first, we are going to see a function that is going to be represent this an. Okay? So an we can represent as a function with n as a variable. Okay, so n equal 1. This is half. This is the 2 over 3, 3 over 4, and so on until 7 over 8. And maybe we can see it will also getting closer to this line. And remember, when we did this, and since this is the topic, the title is limit, then we can try to take the limit concept to try to define how we can take this as close as much to this line. Okay. So if we take the limit for this n, as n is getting large, and then taking over here like this, and we know limit from our calculus 1, I hope you still remember. So we can define with n, so we have 1 over n. Let me write here. I think it's not in the center. Okay. It's 1 over n. Okay. And 1 over n, for n is infinity is 0. So we have this is going to be equal 1. Which is, if we see that through our graph, that it's true. It's going to be close to that line, right? Or close to this number 1. Okay. So by intuition, or with intuitive definition, we could say that the limit for n approaching infinity, or getting large and large and large, for a sequence an, this will equal L. So it means, okay, if we take n large or sufficiently large, and if the limit exists, okay, so the limit exists, then the sequence converge with this value L. Okay? Or if the value is dispersed or diverges, then the sequence is divergent. Okay? Or we say it's going to be infinity. Or can it be, like, if you see something like, perhaps it's getting large and large, and then we cannot really bound the value, then it will be divergent. Or something like a cosine or sine. It getting 1, negative 1, 1, negative 1 is also divergent because it doesn't comes to close to some value. So this we call divergent. Divergent. So as an illustration, this is how, for example, this is just a random sequence. For example, we have here, it seems it's getting large, but then it's getting close to some number that is going to be consistent. So we say that this is going to be limit close to L. So this is convergent. And the same way with this, although we see some oscillation, but the oscillation will comes up to some numbers which is the L. Okay, so we say this is still a converged limit or converged sequence. Okay, maybe any questions first? Or maybe let me know who has learned sequence before in school. I think high school, right? High school? High school, right? Who haven't learned? 1, 2. Who haven't learned the sequence before in high school? 1, 2, 3, 4, 5, 6. Okay, I think almost 10. Okay, almost 10. So maybe I will add some resources. Some resources in the Moodle. Okay, now let's continue this part. So this is limit of a sequence. And now let me just talking about the precise definition of limit in a sequence of a sequence. So we start by looking at this. Maybe let me prepare this to be here and this to be that way. Okay. So let's see what the precise definition telling you. So first, this is our definition from our previous intuitive definition. Okay. But in precise definition, what we want to do is we would like to introduce to some small values which we call the epsilon. Okay. Remember that in calculus 1 you have so-called the delta epsilon definitions, which you probably confuse and you never knew what is that. But it is actually important to know that because in limit, again, if we talk about limit, we need to know, like if we say something is close to another object, how close it is. Mathematics need to know and need to mention that in an official way in their definition. So that's how we end up with this epsilon. Okay? We need to have some small value, which we usually use the epsilon. Okay? So basically epsilon, if we have, for example, here, the L here, nearby this L, we have some distance here, and imagine that this is very small. Okay, this distance will be epsilon. Okay, this is epsilon, and then what it says is if the so for every epsilon that is positive, there will be some integer n such that we say integer because this is a sequence, so we only consider n 1, 2, 3, 4, and etc. Okay, so we say that if some n is greater than this integer, then the distance between the an minus the value will be less than epsilon. So what this going to be relevant is that there will be small numbers that is really small, and this is how we are actually telling you that whenever we talk about limit, it's never actually the real numbers. It is close to something which is really small than any small numbers. Okay? This is really difficult to say, but this is actually giving you the idea that there will be a very small numbers. So whenever you change your n, the small numbers also changes. Okay? So this is how actually it applies. Okay? So this is going to be some epsilon here, or if you want to draw in the graph, like here, for some integer n, okay, if you have some n and you see that, let's say we have here is our two green line, which signifies the L minus epsilon and L plus epsilon. So every time we change the positions, the epsilon also changes, and the line also changes. Okay, and yeah, I think that's it. And for the infinite limit, we also have this definition. And basically for the infinite limit is we are going to have a large number, and we cannot control. It never going to be converged. It will be going to be large and large and large. Okay? So it means that the limit is going to be infinity. Okay? Now, the precise definition is that the n whenever it is greater than the integer n, the capital, the an is always greater than the capital M. I think I forgot to put into the, okay. So it means that the an will always greater than any values that we set. It means that it's going to be increasing, increasing, and increasing. Okay. Now, the infinite limit, for example, is something like this. This we call infinite limit. And this is another divergent, not infinite, but it is diverge. Okay. So this is divergent sequence. Something that is oscillated, and we never conclude what it is. It's never going to be in one value. The other one is going to be increase and increase, and we are unable to control. We cannot control. So in A, this one here, it oscillates between two numbers. And this one is going to be larger and larger. Okay, and since we are discussing on limit, then we are going to have some properties. Property of convergence sequence, which the convergence sequence is by taking the limit. So all things here, for the limit law, it will be exists. And I think if you understand very well for the limit, this is the same with the limit property you have in calculus 1, okay? So nothing really new, and nothing really new. So if we take the power, we can take this sequence and then take the limit inside. Yeah, practically the same limit law. Nothing really new. So we can just review, and you can review your calculus 1 limit notes. And also, aside from that, the squeeze theorem also we can try as well, as long as we can define all the sequence in terms of that inequality. So we have AN, BN, and CN, and if the BN is in between, if we know the limit for this and we know the limit for this, then we can for sure state the limit in between. Okay? It will be the same, right? The limit L. And no, of course, by looking at the graph, you see that it is going to be converged into one value. Okay. Another theorem is this: if limit for the absolute value AN is 0, then the limit AN is 0. I think that's all for the sequence, the introductory for the limit. Okay. So basically, solving the sequence, basically solving using limit. So every limit theory is going to be works. For example, if you see the 0 over 0, then you can try L'Hopital rule. You can directly use that. and you can use many I think different way to as long as it is suitable for limit. Okay. How about for example here, okay? How about if we have the limit so whether the limit exists or not. So we have -1 with power of n over n. This is particularly, we are going to use the theorem here. Okay? So we are going to take this in absolute value. And we say that limit of 1 over n is going to be 0. So this will be exist and it will be converged at 0. But of course we need to know like whether it's going to be converged or not, right? We need to convince ourselves whether this is true or not. So we can try just build our graph. We can start taking, maybe let me bring here. So let's say this is the an and this is n. Let's say this is 1, okay. 1 and then 2, 3, 4, 5, 6, 7. Let's say it's 7. So if we have 1, it means we are going to have -1. Okay. So let's say this is 1 for an here and 1 for -1 for that. So we start from here, right? And then n equal 2, it will be positive half. So 2 will be here and that is 2. And then 3 will be a negative. So -1 over 3. 1 over 3, perhaps it's going to be there, maybe here. And then 1 over 4, it's a positive, so it's small here. And you will see that it's going to be getting closer to 0. So here is another one here, and then you will see that it is going to be closer and closer. Oh, perhaps it's not there, it's supposed to be here. Okay, so it's getting closer to 0, right? Which is true from our calculation with limit. So I forgot to write one theorem here to copy. So if limit as n approaching infinity, an equal L, and the function f is continuous at this L, then we say we can use the limit to evaluate the function of an, which is going to be function of that L. So remember that we need to have this as a continuous at this L, okay, at this L. Okay, one last thing before we end our lecture. Just an example here. Sometimes you are asked, for what values of R is the sequence R with power of n converge? So if we check through our definition in limit with the exponent, we get the idea that if we have limit, we take the limit to infinity. For exponent b with power of x, this will be equal with infinity. This is for b greater 1. Okay, and then limit equals 0 for a number in between 0 and 1. It means a fraction, okay, a fractions. Well, you could check using the e with power of x, if you see. If you have e, you have that. So you can see that it can go for infinity for b or greater 1. This is for e. But you could also see that we can have the negative x like that. This is, for example, this is, let's say, b with power of x. This is b with power of negative x. So negative means that it will be in a with a fraction. It will make it into 0, right? Okay. Okay, I hope that is understandable. So the same way we take for r. So limit for this r, we can have two choices here. So r is greater 1 and r is in between 0 and 1. And then if we take the negative 1 less 0 less r less 0, then we could take the absolute value and we switch this 0 and 1. So we can have limit which is going to be 0 as we did in previous slides. So by the end of the day, the limit for r with power of n will be 0 and then if r is less equal negative 1, then the sequence Rn will diverges. And I forgot here, we can write first to check every, so check when r equal 1, this is 1, and then when r is 0, this is 0. And you can see the conclusion and the graph through here. So this is for 0 less r less 1. It's going to be here. And this is for r equal 1. This is r greater 1. And this is for negative 1 less r less 0, which means we have a fraction that is negative fractions. And we have, this is going to be the r less negative 1, which we have here and going over there. Okay. And as conclusions, we have this. Okay, so the limit as n going infinity for r with power of n, it will be 0 or 1. So it will be 0 if we have negative 1 less r less 1, and it will be equal to 1 if r is equal to 1. So outside of this, then it will be differed. So this will be converged between here. It will converge here and diverge for other area. But within this convergence, it can be 0 or 1. Okay, now to end the lecture, I will